Hi, this is Wang. I am a research scientist at CSIRO State 61. I'm going to present our work, BulletCT, towards more scalable ring confidential transactions with transparent setup. Our contributions are twofold. First, we critically examine a recent proposal from SMP 2023 that integrates an any-out-of-n proof into ring confidential transaction schemes. Through our analysis, we uncover several limitations of this approach and argue that k-out-of-n proofs offer a more practical alternative. Second, we introduce a novel k-weight-based k-out-of-n proof alongside a new tag proof that enables linkability. Together, these components form a new RingCT scheme that achieves improved scalability, reduced communication overhead, and greater verifier efficiency compared to existing solutions. Let me give a brief introduction to the background. Blockchain leverages cryptographic techniques to link blocks together. Blockchain enables decentralized peer-to-peer transactions without using a central authority. The technology has spawned the creation of various cryptocurrencies, such as Bitcoins and Ethers. Each block consists of a multitude of transactions, where each transaction contains three key data: a sender's address, a recipient's address, and the transfer amount. However, blockchain does not provide privacy for transfer amount or anonymity for transacting parties. Particularly, blockchains suffer poor scalability. Scalability refers to the processing capacity of transactions within a specified time frame. Privacy, anonymity, and scalability used to be the two major bottlenecks of blockchain systems. The emergence of ring confidential transactions addresses the privacy and anonymity issue. Let us see what are ring confidential transactions. In normal transactions, like Bitcoins, both the transaction amount values and the transacting parties are publicly visible. In ring confidential transactions, the transfer amount values are hidden from outsiders, and the transacting parties are mixed up with a set of ad hoc group of users to ensure anonymity. RingCT schemes are protocols that support confidential and anonymous blockchain transactions. RingCT signatures play a vital role in ensuring the integrity and anonymity of RingCT schemes. Existing efficient RingCT schemes are in the discrete logarithm setting without using a trusted setup. Existing DLOG-based RingCT signatures consist of two key components: a k-out-of-n proof and a tag proof. The k-out-of-n proof allows to prove the knowledge of k-subset secrets hidden in a public key ring. The tag proof allows to prove each of the k tags is linked to one of the k-subset public keys. The tag proof is used to prevent a public key from being used more than once. For example, given a ring with 8 public keys, a user can prove the knowledge of the secrets hidden in the public key P3, P5, and P8 without leaking which 3 public keys. The user can also prove that the 3 tags share the same secrets with the 3 public keys without leaking them. Typical examples of DLOG-based RingCT schemes include Monero, OmniRing, RingCT 3.0, and ZG SX23. However, all of them still suffer from scalability issue with either large communication costs or high verifier costs. Here's a normalized comparison of various RingCT schemes in terms of communication costs and the verifier complexity in radar charts, where the vertices closer to the center the higher efficiency. We can see that BulletCT is positioned at the innermost part of the two radar charts, demonstrating superior efficiency in both communication and verifier. The other three exhibit different trade-offs in either increased transaction sizes or reduced verifier efficiency. First, we analyze the use of an any-out-of-n proof in RingCT schemes as proposed by the recent work ZGSX23. Their approach introduces a k-weight technique that employs a bit vector with Hamming weight k to compute a weighted sum over the public key ring. Given an n-sized public key ring and an n-sized bit vector, where Si is the ith secret key, we can use this bit vector to extract a weighted sum on the right-hand side of the equation. Given the random challenge Y, knowing this weighted sum means knowing all the k hidden secrets. Notably, using the any-out-of-n proof can hide the number of non-secrets k to provide stronger anonymity than k-out-of-n proofs. However, we identified several limitations of applying any-out-of-n proofs in RingCT schemes. First, although hiding k can enhance anonymity, it requires RingCT schemes to use n tags rather than k tags, where n tends to be far larger than k to ensure strong anonymity. So the size of tags becomes the dominant contributor of the total transaction sizes. Secondly, storing n tags places a significant burden on blockchains. Thus, ZGSX23 proposes an accumulator-based tagging scheme that enables a stateless blockchain architecture to reduce storage overhead. However, this introduces new trade-offs. On one hand, the benefits of stateless blockchains over stateful ones remain controversial. On the other hand, using accumulators adds extra cryptographic complexity. We primarily describe the techniques of our tag proof. We use an equation where we raise the k's tag to the power of y power phi k, so that the same weighted sum can be extracted from both the n-sized public key ring and k tags. However, it lacks a necessary constraint to ensure the k's tag is indeed raised to the power of y power phi k. So we use an equation to impose a permutation constraint on the exponents of the tags. If the tag exponent vector alpha k is a permutation of the vector y power phi k, and the weighted sum extracted from the public key ring is equal to that of the tags, we can conclude that the secrets hidden in the prover non-public keys in the ring are a permutation of those hidden in the tags. Thanks for watching. Please visit my homepage to learn more details.